Hello everyone, welcome to this lecture on advanced heat transfer modeling. This particular lecture will be focused on solar load modeling. This lecture is a part of the advanced heat transfer course, and this will teach you how to set up the solar load model in Fluent, what are its different applications, how to use it, how to post-process, as well as a case study related to solar load model. So before we move on to seeing the solar load model, we will have an overview of how do we end up actually having a separate solar load modeling concern, or why do we actually need to consider solar rays and its effects. So solar radiation is a significant source of heat, that is a well-established fact. Now there is also going to be outdoor-indoor ventilation problems that we deal with, where solar load or solar rays are going to be of critically important, and we need an accurate and effective way to include heat from solar radiations. If we neglect it, we are actually neglecting a large part of the heating effect and for that particular problem. And we need not model radiation all the time, so that we need to avoid radiation modeling. And domain size, however large we consider the solar radiation, becomes that much larger heat component. So domain size is also a concern, and location and weather parameters also affect what sort of solar heat is going to come up. So we need to know knowledge of location and weather conditions as well. They are critical parameters. So why solar loading is important, and why heat from solar rays is important? Heating due to incident solar rays is very common, but a very important phenomenon. It is observed everywhere, but the effect of it is very important as well. A lot of energy is radiated by sun to our planet, so that is part of that energy is going to be important when we consider solar radiations. Due to solar radiation, temperature rises during daytime, and during daytime the sun rays are a critical heat component, or they are a critical effect when we want to consider heat. And this rises in temperature accounts for majority of the flow occurrences. Because of that, there is natural convection phenomenon occurring, and it plays a very important role in industry-oriented research and optimization studies if we neglect it and if we consider it. So there is a large amount of difference if we neglect heat due to solar rays, and if we include heat due to solar rays. Applications are wide-ranging. They are a heating effect due to solar radiations is important automotive climate control. It is important human comfort modeling in buildings. It is also important HVAC modeling and greenhouse modeling. Solar load model is activated after activating the radiation model. This is what we need to consider. So whenever we see that solar load model applicability, the solar load model is activated only after activating radiation model. The solar load model is used to calculate radiation effects from sun rays which enter the computational domain, that is for CFD, and it is only available for 3D cases. It can be used for both steady and transient conditions. There are two algorithms in Fluent that are considered for solar load modeling. One is the solar ray tracing using tracing algorithm, and other is the discrete ordinate DO radiation model. And in the DO radiation model, solar load are applied directly into the DO model. Now solar ray tracing, we will have an overview or introduction to the solar ray tracing model. External radiation source effects are included in the thermal energy equation in the solar ray tracing model. This is what happens. There are collimated beams of radiation that are considered, and semi-transparent walls are considered, and depending upon the transparency of the wall, this ray tracing type of algorithm is used to know where the solar rays will be incident, and that much amount of heat is put into that incident cells. When these collimated beams encounter an opaque wall, their energy is input into those wall faces. So this is what basically happens. Whereas the DO model, now this DO radiation option is available with the discrete ordinate radiation model. This is the pictorial representation of that. Radiation flux is also available for semi-transparent walls. So even for semi-transparent wall, radiation flux is considered, unlike the solar ray tracing model. There is a DO radiation transfer equation that is solved, and actual radiation transfer is solved rather than just solving ray tracing algorithm. Modeling steps is pretty simple. We select the solar load model in the radiation model panel. That is, if we go here to models, radiation, and we activate the solar ray tracing model if we want to select the solar ray tracing model. After this, the solar load parameter panel will open up. This is the solar load parameter panel. We set the position of the sun in this particular area. Then we set the direct and diffuse solar irradiation values here. These are the direct solar irradiation, diffuse solar irradiation values as an input. After that, the most critical part is the solar calculator. This solar calculator helps us to find the position of the sun. The inputs that are required is the global location, orientation of the object that we are going to consider, where we are going to do CFD modeling, the actual location of that, and the day and time of the particular day. Using these two parameters, what the solar calculator does is that it decides the position of the sun. And this is a very realistic position that is available at that particular time, location, and day. So modeling approaches set up the solar load model, give the boundary conditions. Important wall boundary conditions are semi-transparent walls, whether they are opaque walls or semi-transparent walls, and optical properties of each zone. The solar load model is based on using the energy source for every phase activated for solar load. So what it does is that wherever the opaque walls are there, the solar rays hit them, and there they deposit their heat, and that heat is deposited as a source into the phase for which we have activated the solar load. The model plus this energy the model puts this energy as a source term into the adjacent cells, and order of priority is first for shell conduction, then for solid cells, and then for fluid cells.